You want me to shut after the mic?
Start
You guys are going. Estamos haciendo algo específico para uno y que debe ser entonces que vayan siendo comparando todos. Pausando un poco mayor y el justo no cuando que guarde uno anterior. Entonces no se queda cuando va a encontrar un So, do you think we're going to kill them?
I do want, and I think let me see if there is a pull request. But there isn't.
So let's look at the meeting.
Yeah, so you have Telegram?
Estamos haciendo mal.
So we're going to start with the second part of this class, but before, maybe we wanted to just quickly check back in with you to see if there was any questions about the first part. So if you didn't finish this exercise, that's perfectly fine. If you are very motivated to go home and do it another day, or it's a great exercise. But yeah, if there's any questions about this part, we're going to go in the next part more into how to write tests, and there's going to be some other exercises on how to write tests. So maybe some stuff will also become clear. But up to now, is there any burning questions?
How can we define the test?
How can you define the test?
So set of tests we have to add.
So there's, you typically would have a file which is called test_my_functions or something, and then in that file there are some functions that are called test arithmetic or test sum or something, right? And these functions are what's run.
Or you mean how do you figure out which test of session?
Okay, sorry, I'm confusing myself.
That's exactly the
But
second.
this is the second part. How do we what do we
Right
test?
room.
Thank you. Okay, so we're gonna look at some testing patterns. So some common cases that might be testing, and yeah, just look at some examples. So first of all, what is this test supposed to look like? So kind of the infrastructure, the architecture of the test. I mean, some features that it should have is that it should be short and quick. In the break, I was just telling someone about the tests I wrote just after I had this class for the first time, and they took, like, the test suite took multiple days to run. It's probably not so great. You want to be kind of continuously running them while you're programming them, and then changing a thing, and then running your tests. So if your test suite takes 10 days to run, it might not be so useful. It should be easy to read. So at a first glance, this is a little bit also related to the question about whether you should have multiple different assert statements in the same test. So ideally, one test does one thing, and it's very easy and quick to understand what it is. The name will hopefully tell you exactly what it does, and it should only be a reasonable number of lines. And things that should be avoided is something like loading your entire data set into your test. Probably takes 3 minutes to start with, just loading all of that data in, and then when that data then changes, then your test might change as well. So try to avoid this and try to instead use little tiny miniature cases, kind of toy examples of problems that might occur. And then, of course, messing with anything that's live and online, also typically not a good idea. Right. So, what does it do? Usually, it's kind of reconstructed at these three points. First, you have the given. So, what is the input to your function? You have the part where your function is called with that input, and then we have we know what we want to come out of the function, and then that's the assert statement where you say the outcome of the function is equal to what I was expecting to see. So that's kind of the generic build-up of the test. And then now to the question that you asked, what should we actually be testing? Well, usually it's good to start with a simple and general case. So and try to reduce all of the reduce the complexity to like the minimal version that's needed to test the thing that you're interested in. So here's an example. So here we're testing whether the string, we have a function that checks whether so this function is now making a string all lowercase, and we're giving it a string that is not all lowercase, and what we expect to come out is the string in all lowercase, and then we assert this. So this would be kind of a generic example of a case that we might want to test. And then, so after you've tested this generic thing, we can start testing the boundary conditions. So, for example, what happens when we give this function an empty string? We would expect probably to get another empty string back out and not anything else. So then test these edge cases. So maybe also another case would be a string that is already all lowercase, and then whether it still comes out as lowercase or whether. Yeah, so other things would be a string that is already lowercase, or something that has strange symbols. I don't know. Am I in the way of the beamer actually? Yes. Great. I might just move over here. So now if we are, I mean, we just said it's typically we would have separate tests for testing each feature. But if we consider making something lowercase to be one feature, then maybe all of these tests could be collected into one. So here, what's happening, or one way of doing this would be to kind of collect your test cases. So this is always the input, a tuple, so it's a list of tuples. And the first part of the tuple is the input. And the second part of the tuple is what we expect to happen. So we can make a list of these test cases and then loop over the test cases, always asserting that the output is what they expect. There's actually a nicer way of doing this, which allows also then the output to be a little bit more readable. So if I do this and then one of them fails, then it might be tricky to figure out at which iteration of the loop did the failure actually happen. I have tried to help you, but there's a nicer way of doing it that I want to show, which is called parameterize. So this is a decorator. So this is our function, our test addition increases function. This is our test, and it asserts that if I add something to 5, it gets bigger than 3. And this thing on top here is called a decorator, and it's a nice little feature which allows you to kind of do all of these test cases all in one convenient bundle. So what's going to happen is that each of these values in turn gets put into this variable A, and then it asserts it. And maybe we can just quickly try to program that. So this is just an editor. I was informed, but it's black and white. I was not expecting to do this one, but I was told that it would be good to see some people working in the editor as opposed to in the terminal the whole time, just so see the variance of ways to program. So I hope that this is how it's readable. So I'm just going to make a test file, and I'm going to do my test. Because we need it for that decorator too. My test function is going to be test. What are we testing? Nice. And then we want to assert that if you add anything to 5, it's bigger than. And so in the original cases that we looked at, we would look something like this. So I'm just going to save this in. So now I'll go to the terminal. Now I get to my folder. And now I'm just going to break quickly. You don't need to do this part. This is just me setting up my environment. Okay, now we're at another state. So then I'm going to go type test. What was it called? Test sum. And so this passes. Right? I'm sorry for the colors. I did not make this. So now if I wanted to do it with the parameters, what I would do is go try test mark, go to parameters. And now it gets passed with a string that's called like a variable, and all the. Actually, I'm going to just double check the screen. So we have the name of the variable that we're passing in, and a list of all the values we wanted to take on, and the variable gets passed into our test and gets used here. It's not a list. Okay, I'm sorry. It gets passed more than list. Just like this. And now you can see that it actually it passed 5 tests. So we do verbose. Now it the output that it gives you, it tells you it tested this same test 5 times, and this is the input argument. So this is kind of a nice way of collecting a bunch of tests into one structure where you don't have to rewrite the same test a bunch of times, but you're testing a similar. Is everyone happy with that? So yeah, so we can use this for either doing. So this is the case where I have one variable going in, and I'm just tempting changing this one variable. I can do the same thing for with 2 variables, right? I can so here I'm giving it the string of the 2 variables that go in, and these are my test cases. So hello world in this strange compatible version, it gets put into the string argument, and the small version is the expected version, and so it would run for all of these 3 test cases. By simply having 2 variables here. So you can use it. You can use it to really connect them. Okay. We're gonna move on to the example that we're gonna be working with for more or less the rest of this section, and it's the logistic map. So I don't know how many of you have heard of the logistic map. A couple. Okay, so it's an iterated function that or the version that we're using is an iterated function, which has often been used to model population growth. So within I'll show the function in just a second, but for now, let's say I have some population text, and if it's smaller than some value, then as we kind of move through generations, the population will rise up to some level and then stop. And then if it starts out at being above that value, slowly what they call the starvation mode, population decreases until it reaches this stable point. Yeah, and if you already start very close, then it also just converges. The function looks like this. So it's R, which is the rate, times X, which is the population at the time, times 1 minus X. And the way an iterated function works is you put in that first value of X, so X0, and put it into the function, and then you get out the next generation's X value, where X is a number between 0 and 1 that represents the ratio of the existing population to the maximum possible population. So that's the definition of X. But essentially, you just stick, you put a value in, you get a value out, and you put that value back in. And then you get another value out, you put that value back in. That's how an iterated function works. And this rate parameter here is what makes it either work very well as a population model or work not very well as a population model. Or work not at all like a apocalyptic population. So the logistic map is interesting on one side as this population model version, but also it has some interesting chaotic behavior that occurs under a certain value of R. And yeah, we're going to experiment with it a little bit. But so let's say we've implemented this iterated function, and we're going to do it in a minute. But if I just wanted to check that it was working as intended, and just looking at kind of these behaviors, is there anything that kind of strikes you immediately that you could test? What tests would be good tests that this thing is behaving as we expect? Sorry? Sorry, I didn't hear.
We have 0.
We have 0. Yeah, if you put the number 0 in, yeah, sure, then if it starts out with population 0 or if the rate is 0. Oh, I guess would be good test points, yeah. You said that it converges, so I agree that like under these values where we expect it to converge to the current value, it would be good to check that our does. Any other ideas?
Only values
Yeah, we could test that it kind of ends up going down. Yeah, there's actually so in fact there's for the logistic map there's some actual mathematical properties that that are defined that we could test those that they have in our implementation as well. Yeah, so we're gonna just start with this little project. It's actually in a different repo from the one you were using before. So now we're in 2023 Mexico testing project. And the idea is that we're going to implement this iterating function. This should be a fairly quick thing because the function literally does this. This is all that the function does. And then, yeah, more instructions are also in the README file, and we're going to use some time to get started with They're going to be working on this for a while. If they want to switch, so maybe actually we forgot to say that you can switch partners.
Yeah, so I should pause cloning right now. I'm really sorry. And rotate.
Everyone's cloning stays and everyone else goes to find someone.
Yeah, new partners and ideally new geography in this case.
If you don't have a partner, can you raise your hand? There we have. Excellent. You're supposed to read the repeat. This is not all the information you need. There's a lot of important information in the repeat. That's why I removed it now. Read the repeat.
So let's go ahead and Yes, for example, we had So I can show you some solutions unless you're all really excited about finishing it by yourselves, or otherwise I can live code it.
We already have a solution.
You have a solution.
Yeah, but we have a solution.
Okay, so then I think unless anyone shouts at me, I'm gonna just show some stuff. So. And Facebook circle death. So I'm just going to show you what this thing looks like in my Finder here. So we have the projects, and in it I should have a function of a file that's called logistic. This one was in here before. There's the README. There's my temp, my new and fresh. That's the file that I have so far. And then in my logistic.py file, there should be a function f, which does what? Yeah, it computes new x. X, well, yeah, x plus 1. Yep. So what should I type? Exactly. So this is literally just, I mean, we can also immediately return it. We don't even need to write it to any fancy variables or anything. This is and then maybe I can do this away, but from scratch. So then the other thing that we wanted to write was a function iterate f, which essentially just goes through multiple generations and puts the result of the population size at that generation into a list. So here what we do is we pass into the function a number of generations, a number and an xi to start at, or an x0, then and the rate r, and then the way it's implemented here is that I have a for loop, and then the for loop iterates over the number of iterations that I've given. And then this is, so this underscore is kind of a shorthand for saying I don't need a variable here. It doesn't matter. I could also have put I and just never used it. But some people like to put the underscore instead to just indicate that this is a variable that I've never ever used. And then, so I compute x by giving into our function f, I'm giving into it x and r, computing it in x, and appending it to my list xs. And then some people ran into this, that eventually for testing, it's going to be useful to have it be a Numpy array, because then you can compare lists. This is kind of optional. You can also do this in the test depending on the design decision. Is everyone convinced of this solution? Yes. Good. Okay. So now let's go to the test. So another the first thing that should be in my test file is my imports. And I think I somehow in my mind you had already learned about importing things, and you hadn't, and that's absolutely my fault. The way that that you're going to learn a lot more about importing tomorrow, but the idea is that if you have two files that are just right next to each other, and one of them is called logistic, and it has the contents of one function that's called f and one function that's called iterate f, the way that you can use those files in another file, for example, your test file, is to go from logistic, import f and iterate f. So you're importing those functions from the kind of next to it file to this one. That's that. We need those because without them, we need to have them to test. And then for later on, I'm going to need the PyTesting to start all those. And the PyTest is relevant for our parameterize. And then, so let's look at the test without the parameters first. So we have the test gets passed a value of x, so the starting value of x, the r, and the expected outcome. It computes it and then compares it. In this case, I think this is also just use a regular search, right? Because we use these close, right? Okay. Nope. What's the keyword there for a surface space and list? For example.
It's closest from the math perspective.
But no, I also yeah, we can. There's these things exist in multiple things. The one we used before, it's true, it was from math. And then we can compare results. So so now we have this, and I'm going to go to the terminal, and I can go, and they pass, and it's 3 dots because I'm doing it for these three cases. The 3 cases that are also in the README, and I saw some people were having some trouble with the exact syntax of the parameterize. It's a bit not obvious why this would be a string separated by commas, but this is life. Just how it is. But once you figure it out, then it works. Right? So how many people got to this point of testing this first thing? All right, about half. If the half that didn't get to this point, are you happy about it? Happy about the solution? Like, do you agree with this? Do you have any questions about it? Do you have any comments? how this should be better in the future. Or,
I have one from a tutor point of view. I actually wasn't aware you could use multiple commas, and I think the only examples that I have seen parameterized in the docs only use one. So I got stuck trying to give a complicated solution where the inputs were two, and then we had to unpack the two. So that got a lot more complicated.
right. Right. Yep.
That's
I think we at the end we put this we put it up on the screen. We have it in the slides. So this passing in multiple arguments is in the slide. Yeah.
Can you use the like the smart parameterize multiple times? So it's just for one.
A very good question. Yes, you can, but that does something slightly different. So if I were to, so let's go back to a very simple case. So let's say def as sums. And we're going to test that A plus B is larger than A. And then we have input arguments A and B. And now I could use parameterize in much the same way, where I go A and B. So so this would be exactly what we were doing previously. Sorry, I got bigger. So if you wanted to stack it, it would work like this. So you would have the first and the second. This one would be A and this one would be B. Oops, 4, 5, 6. What are you complaining? Questions? Yeah, so what this does now is it does all the possible combinations. So let me comment out the rest of the stuff. So in some cases, you might be interested in testing kind of all the permutations of different things. And then this is then what you would use the stacked parameterized. But if you have a set case, like a set stack of given and expected, then probably the others, this version of it is what you want. But so this is more when you're testing a concept, you're testing like addition works or something. Like you're not, if you want to test a specific value comes out, then yeah, this piece. So this is neat, and to make you go a bit power hungry, which is what happened to me when I was testing this thing that ran over multiple days. I was testing all the different permutations of all the parameters, like a crazy person. So I'm just going to show the solution for the second part, which is testing the iteration. And just in the same way, we had our given arguments and our expected things, and we give it to parameterize in this syntax that we want. And now the test uses our iterate f function, which returns an array in my case. In your case, it might be a list. If we're returning a list, we need to convert it to an array to do this element-wise comparison. And then, yeah, we're just comparing. Yeah.
We use
So,
the
yeah.
assert array almost equal instead of assert of
That's perfectly fine. There's like we said, there's depending on which package you're using your testing function from, it's going to be called something slightly different. But so they all do more or less the same. So one thing I really I wanna get to next is that you may have done all of this, and you have no idea what your data actually looks like, and you've tested things in this very abstract realm, and maybe you've thought a lot about it. But I think one of the most important tests that you could do is to look at your data. And so the last part of the exercise, which I'm afraid we didn't really get to look at so much, was to where is it? Import, and so there's a plotting library that comes that I gave to you in the folder. And we can just use this to kind of explore our thing. I just want to just show this. So it says, important toggle plot trajectory from the in a new script. So I'm going to make a new file. Script.py. And then it says to import plot trajectory from the plot. So import plot trajectory from plot import plot trajectory. So let's open that file up for a second to see. So this is a function, and it has this is the module, and it has a function plot trajectory, and it's plotting something. So let's say how do we call it? Plot trajectory, and then we give it some arguments. So n would be the number of iterations. Let's say 100. R can be 1.6, and we'll start our population. But these are all things that you can take, right? So now I've written my script. I'm going to go back into the terminal and go Python script. It's doing something, and now it has written a file. So if you were doing this in a notebook, you could have the plot showing the notebook. But in this case, this is what our trajectory looks like. So these are my iterations. We don't have. We learned that yesterday that we really need X and Y labels, but we don't have them. But this is this is the generations, and this is the X. And so let's try that again with some different values. Let's say we go into this range that we know is going to behave very differently. And do the same thing. So, and now it behaves like this. And I think it would be a good idea if we just took another like 3 minutes, where you just quickly implement this little script and just run it and just do it for like 2 or 3 different values, and just check out what this thing does.
Yeah, I think, has everyone seen at least one trajectory? Yes. Has anyone not seen any, like, not been able to make any final stuff here? No. One. Okay, I'm gonna come and help you, and then. Okay. Yes, maybe just not worry about it so much. I'm gonna keep going here. Yeah. So we have now use this one extra fun thing that's parameters. There's a couple of other ones of these, and we're not really gonna play with them too much because we need to move along a little bit. But I want to introduce some of them so that you've heard of them before and let them look them up later as well. So one thing that you can do is you can mark something as X fail, which means you expect it to fail. So if you have a test, you wrote it, it's maybe something you haven't implemented yet, something you know should work eventually, but isn't working right now, something that's maybe a little problem, but not a big problem, and you need to fix the big problem first or something, you can kind of write your test, and then mark it as pytest.mark.xfail. And then you're kind of in your output, it's going to look that's logistic. So now, if I had this one and I marked it as and then I changed this so that it's wrong, right? Wait, it's fine. It's the altitude here.
No, that was closer. So now you see that all of these ones, they are marked as X fail, but they're not really showing up as red, and they're not giving you all the error output. So yeah, this is one nice extra feature. Another nice extra feature is skip. So if you don't like X fail, if the test runs, it just if it fails, like when it fails, it doesn't give you any of the errors. And if you mark it as skip, that just doesn't run at all. So if you have something that want to skip, I guess that marked on skip. And you can also mark things with something else, something that you decide for yourself. So you could have some nice syntax like I only want to test. I only want to run the test that I have marked with the mark smoke. So smoke is one that already exists. A smoke test tends to be something just there's a fire and there's smoke. That's usually a good sign if there's something wrong. So smoke tests check for like very basic failure, and so these are tests that should be run at every time you run the test. Whereas there might be some very detailed ones that might take a bit longer, or something that you don't want to run the whole time. So you can kind of split up your tests in this way by giving them markers. And then you can look at the ones that exist. You can also define your own, which is a whole slightly longer process of registering the marks. And so if you're interested, here's the link. The other thing that's kind of cool is that it allows you to do stuff like this. So you can say smoke and not slow. So you can that will run all the tests that have the mark smoke and not the mark slow. So they try to make it nice for you. So I don't know if it was around yet. Is it lunch break time? Right? Great. And it's not break time. Did you finish your copy of the file in the right way? And did you manage to run some of the plots? Okay. Yeah, so to run it, the thing was to make a new file. When it comes to sense. Yeah. And then and now, yeah, now
That's right.
I don't know. I don't know why Visual Studio didn't want to. Alright, so if you change the parameters, you can see how it changes. Yeah, because I was explaining what.
Sí. I don't know. I don't want to mess it up. I want to look at the slide. Yeah, it seems to be.
Yeah, no way. But then this is not very quick. Mine is not.
Yeah, roughly. Okay, that's an important thing. That's actually an important step.
Yeah. You did. No. Oh,
You're balancing that.
yeah, no. I just. Yeah.
Mire, está puesto así, sí, porque este es un curso de vernácula católica. Pero,
Lo podemos montar en herradura.
si están en herraduras,
So setting a seed somewhere in that test that uses randomness is probably going to be very useful. And interestingly enough, this is not something that is very well integrated into the PyTest as it comes out of the box. So yeah, just quickly for those who haven't heard so much about seeds, it's essentially a pseudo-random number which is used as the basis to create all following random numbers. So if I set the seed for my random state at the top of my script and I run it, then it's going to give me some pseudo-random numbers in the script. And then if I run that exact same script again, then it will generate those following random numbers based on the same basis. And so we're going to get out the same randomness in that script. So for everything concerning reproducibility, seeds are very important. And so the minimum viable solution for this would be to simply in your test or at the top of your script as a global variable, right? To just go seed equals something, here's my random state, and then every time you want to use randomness, you use your random state of random. Right? Can everyone imagine what that would look like in their test? So this is kind of the minimum thing. What's maybe can anyone see why this is only a semi-good solution? What could a problem like this? If I always test with the same scheme.
You are having the same randomness.
Yeah, I'm always having the same randomness, and I could randomly have picked a seed that works, but unfortunately other ones don't. So yeah.
Has everybody seen this random state before?
I have by selected different parameterizing models. So you do either root search or random in certain parameters for your model.
Yeah. So exactly. So I think many of you use np.random.random. So when you create a random seed, you basically instead of writing np.random, you write random state.random, and it has exactly the same methods, right? So if there was np.random Gaussian, there would be a random state.Gaussian. So it works exactly the same, but the nice thing is that you can fix the state at the very beginning and then pass it around.
No, that's fine, that's fine. So we're gonna go and do this semi-viable solution first, just to see what that looks like. And it's another exercise. I want to mention that if you didn't finish the previous exercises, don't worry about it. We're not expecting everyone to finish. A lot of this is also for you to kind of see a lot of the things and then know what to look for in the future if it's something that you want to use. So if you haven't finished it, don't worry. And if you haven't finished the base function, so the f and the iterate f, you can find not in the project folder, but in the original testing folder, there's a hands-on solutions logistic fun folder where you can take the logistic.py file. If you're not sure if your solution works as well as you like, you can take that solution and use it for writing the next couple of tests. So the exercise is to write a randomized test, but check for r equals 1.5, any random starting point converges to the so to this stationary value. So any questions? Okay, then. What's that? Person files? It should be in the project. It's still following, yeah. This game doesn't really say much more than it says there, but sometimes things. And the arguments for the other thing that is using is R, which is then instead of passing that text, and what else do they have? Then you go, so, on it, save for random Seetha track. It just be a variable. One line down. So this is not your and now you solve your something else.
So as you guys are writing this test, one thing I just want to note is this is a case where you don't have to use parameterize. It might be better to not use it. You can, if it works for you, go ahead and use it. But be aware that you don't have to use parameterize. So if it's easier to build, if it's easier for you to build the test without a parameterized decorator, don't use it.
And then you can count those how many articles. Yeah, so our next one is so you can give it like this, and then say article that is this goes to this, and then you get true and false, and then you can say are 80% of the valuation goes.
We actually define and also attract.
But then also if one run tests, by the time I was just but then so different things. One is that all tests have to start with tests or the second thing is you have to go and type it. Now, let's see. So you don't need input arguments or only when you need I think we're gonna, I've seen some people sites, and I think I'm gonna live code and show you my solution. So, what was the task? The task was we want to write a test, and we want to check whether the right or something like this. And then what we said we wanted to have a seed, and that seed can be whatever you want. And then we set a random state. How do I, what was the, and B dot random, so that's, there we go. With the Z. And now, we can set an X, or an X0, right? Which, so, the task was to pick, to make the randomness pick your random starting value. So what I'm doing is I'm going to take the random state, so rand, to give me a random starting value. And then, which function are we using to test it? Iterate f. And then a bunch of x values are going to fall out. And what does it take?
Number of iterations.
Number of iterations, let's just say 100, 100,000. Then R, we said X0. And next, R, and what was R supposed to be? And then we also still had the expected convergence point. That was 1/3. And then now we want, what do we actually want to test? No, that's not how you should want the surface ghost. Well, X is now a numpy array. Good point.
-1.
Square bracket -1. Exactly. So now we're checking that the last value, so the very end of our tail of our series, is equal to the value that we expect it to be. So let's see. Apparently I didn't import Numpy at the top. That's not good. So this is why I like to always correct it until there's no more red lines, because it actually tells me cool stuff sometimes. It's close as well. It's a Numpy, right? Okay, test converges. So now I test. Sure, we can do -b. Then we do, so we just want to test this one test for now. Does anyone remember how that works? And now? Two columns? And then the name of this. Paste it. All right. So it passes. Okay. One more thing that I think might be useful to know is some people were trying to debug their tests by using print statements and then not having so much success because, especially if the test passes, but in any case, the print statement doesn't come out. So the solution for this, we had hello somewhere in here. This wouldn't print it, right? And if you would want it to, what you would have to do would be to pass an extra flag, which is -s. Then it still doesn't do it when it. Ah, no, there we go. There it is. So then that's how you get print statements out of your test. If you want to debug by using print statements, that's your solution. Exactly. But so we actually we were saying earlier already. We were saying earlier already that actually this hard coding the seed here, kind of putting this in the test, or even an alternative way would have been to put it at the global scope, right? If I put it here, then it would be I could use the same seed for every test or something. But we already said that this could lead to problems in the future. So put it back there. So interesting thing is that this isn't really a case that PyTest has integrated very well, but we can make a solution. And this is now going a bit into the deeper plumbing of PyTest. But I think it's nice, and I wanted to show you the solution because you might be able to actually just go back and use this if you ever have a problem like this. So what we want for each random test, there should be a seed. And for each run of the test, the seed should be different, but that seed should be printed with the result. So we want to know that the seed, so that at least we can run the thing again with the same seed. And ideally, have an easy way of running with a specific seed. So the solution to this thing is a construct called fixtures. A fixture is essentially just a function that we define that runs before the test is executed. So the thing, so it looks like this. We define a seed, like a base seed at the top, and then we have a fixture, which is marked by this decorator here, which essentially just generates a new random state and returns that random state. And then your test, this, for example, this convergence checker, this fixture is going to be run before every test, before each test in your script, and it needs to be passed this random state.
But you need to store it in a variable or something, because I mean that definition, that function runs before anything.
This one.
Yeah, but where random state ends up like a global variable or something.
So it's not a global variable. It runs. So this thing, every time you run test something, before that thing runs, PyTest makes sure that it runs this thing, and that random state gets passed in.
Okay.
So this is a lot of there's something happening behind the scenes that we're not really going to get super into. I think for the sake of this explanation, it's I think easiest to just accept the fact that this fixture, it creates the random state as you want. It also prints your seed, and then it makes sure that your new function, your new test knows about this random state that it created. And so the next exercise is just going to be you add this same code at the top of your script, this stuff, and make sure that your test takes your random state. And then you don't have to generate your random state inside of your test anymore. You can use this fixture instead.
Yes. Sorry, I have a question. I haven't used this fixture myself. Is it necessary that the variable and the output are named the same? And if not, can you rename the function to make it more clear what is the function and what is the output? I'm not sure what is what here.
That's a good point.
Could it be like set random state as a function name? And then,
Do you remember this?
Also, the function name matches what it was. So that
okay,
random
so
set of variables, you don't even need to define, right?
So if it was called set random state, the function name, if the function was called set random state, that would be test something set random state. Okay.
So what we're saying is that this can be done. Oh, sorry. That's
Yeah, and then I'm doing
So we named some function again, just say that.
well,
That's the sovereign single function.
Now it's the value that has been returned by but that looks like
Yeah.
and then the function that is
Information function.
I think variables. How is everyone doing? Has everyone managed to type this in? No. But you have open One of the advantages of utility with the minus S flag is that now you can use it to actually see the seed that you were using. So once it works, do it with minus S, and then you can see the seed. Okay. So you're actually running it like 10 seconds. Why not? Run 10 times at the same time. Now, actually, since your random, and you're already creating your website, you're always running the same. So, yeah, some people have one option. So now here you have your additional random which alternatively you can also just not have since you're already creating. But so what's the question? Look at the question. Yeah, so the random state is coming from our experience. Yes. This is some of the kind of magic of how this works. High-text now sees how you pass something. What is it? And it goes looks and it says, oh, it's singular. That means I'm going to take what comes out and pass it in and give it that for everybody. It's not pretty. Genuinely, they do that because she doesn't like it. This is how the texture works. And there, that's where you're using the random state to generate your random number. So the random state is kind of two bases. Then you can generate multiple random numbers. And then the other thing is that once you're here, search all of those is for areas, right? You're actually so if it works over time, I think usually the search is closest for individual numbers. Because you're comparing just the last number of the array and just look like one. So maybe the search is close. The search space is close. It's close, yeah, one works. And then I think it was Numpy. Yes. So, actually, just obviate this down. Just a typing exercise. I hope that everyone got it worked now somehow. So I'm going to just show it again. So what is it today? I think I'm just going to take this thing and copy paste it. I have the luxury of doing that. And I'm just going to put it at the top of my file here. So setting my seed, and I have some strange thing here. Okay. Here. And then right, okay. So now I've defined my fixture, and now I can go back here and I can put my random state. Some people were complaining that this is the same, the name of the output of that function is the same as the name of the fixture, and that's confusing. I agree. It sucks. That's how it is. Sorry. So you get the random state here now, so we don't need to set a seed here, and we don't need to set the random state here. It just comes in, it just gets passed in. So now we can run it again. But that was all that I intended with this exercise. I'm gonna just very briefly show you this thing on steroids that we made at one point when we were actually coding the programming, the infrastructure for the programming project that you're going to do in the next days. Because I think it's going to be useful for you to use in the future, and let us know it exists. And that's the following. So, PyTest. I'll make this bigger. PyTest. PyTest is this creature, which you can call from your command line, and you can give it some options, some of these. So you can put B for both if you want more. We can test, show print statements, and then what does PyTest actually do? Well, so first of all, it goes and looks for what is relevant for it. So it goes and finds all files that you can test. Within those test files, it goes and finds all the functions that start in tests. But it also does a couple of other things, which is it loads these configuration files. One of them is called conttest.py, and that is a special file that needs to have this exact name, and it needs to be the exact folder where your PyTest is supposed to run. And this is usually where you would define fixtures. So if you can imagine you have a very, very complex setup, you want not only to run the random state before everything, but every time you run a test before, you also want to confirm 3 different things and make sure that some setup has been done. Right? So this is all stuff that would go in here. And then there's also the PyTest.ini, which you can use, I think, maybe to configure like what your output looks like and this kind of thing. So maybe if you imagine you were a company and you wanted every time your company test suite is run, you want your company logo to also show, this is also possible. So there's all kinds of crazy configuration options here. And all of that gets stored in these extra files. So what happens when you run PyTest is it finds everything that's relevant, and then it runs setup fixtures, then it runs the test, and then it runs the teardown fixtures, and then it goes again. So this is kind of the idea with the fixtures. Then when we decided we wanted to fix this randomness problem for us, we had this idea that it wouldn't it be nice if we could not only have a fixture that generates a random state before we tested them, but also that if we then find something is wrong, that then we can take the seed that we know and then put it back in and tell it run the test with this seed. And this is, of course, I mean, already quite a complex scenario, and I'm not going to go through exactly how it's done. I'm just going to tell you that there's a file in that folder that you have called conttest example. And if you simply rename it to conttest, so it needs to have the exact name conttest to be executed. But in your name, you have conttest example file. And if you rename it, then it's actually going to run in a nicer way, and it'll just quickly show how it works. In my test logistic, I'm just going to delete or comment out this fixture. Oh, you don't what? Oh. Why? Yeah, so here in my folder, I have a conttest example. I'm just going to rename it to conttest. That's it. I can show you the contents. It's this. So we're adding an option to set a seed, just on a very rough level. Then we're configuring my test to do the thing. And then we're defining the fixture. So this is the same fixture that you've seen essentially. Uses the seed. Don't worry about what any of this means. This is just a file for you to maybe use in the future if you're excited about random testing. But so now I have commented out. I'll go back to the Finder. Is now that I've given it the correct name, and I've commented out the fixture here. I can still put this random state into the argument of this test, and then I run it. Okay.
That's using random, just
where? Ah, there. Okay, exactly. And now it says it's using random seed. This is a random seed. And now if I want to run it again with that exact seed, I can go -10 seed and then give it that seed, and then it runs in the exact same way. So this is a present from us to you for your random testing. Exactly. Just because we were talking about the logistic equation, we're going to skip a couple of things because we want to show you the continuous integration. Another thing that's in this folder, in case you got excited about the logistic function, is so the logistic function, it with different values of R, it has these different interesting behaviors. So with a value of 3.1, you get this behavior where it's kind of jumping between two points. Then you can have behaviors where with a value of 3.5, you have jumping between 4 different values. And one of the other exercises would have been kind of test find whether it's finds multiple corrective characteristics. Then there's some values that generate chaos like this, and then there's some. So as these values get higher, there's more chaos. But then also, even in these higher values, there's islands of stability. And one nice way of visualizing it is this plot, which there's also a function in the plotting module that lets you make a plot like this. What does it mean? There's on the x-axis, this is a plot that we didn't update after so on the x-axis is R, and on the y-axis is the detractors. So given about an R value of 2.6, the logistic function converges to this value. And then as we start to get into the 3 point somethings, there starts to be two. There starts to be two attractors, and then you have 4 attractors. And then what's just kind of fun is that there's these areas where there's crazy amounts of attractors, basically, not really converging to stable behavior. But then here, for example, again, we have some behavior that's interestingly stable. So this is just to round off the logistic equation topic. And let's get through this. And so testing. To round off the topic of testing, this is due in this is due now, and that's due in 2024. And testing saves your future self some trouble. So your future self is going to thank you. And so in the moment, it gives you confidence in your results, and in the future, it saves you a lot of trouble if you ever have to use it again. And if by now you're thinking, well, that's all very nice, but it doesn't really apply to my code. My code is way too complicated, or there's no way of testing this thing that I'm doing. Then come talk to us, and it's going to be. I'm sure that we're going to find out a way of also testing. So yeah, that's the end of testing, and we're going to move to continuous integration. Hold on to your horses. If I can find it. We're back online. Continuous integration. Well, maybe, does anyone, first of all, have any questions about the testing? Yes.
I test pictures that the other folder began to
So, yeah.
Tempter. PyTest has a built-in fixture called Tempter, TMPDIR, which is, at least for me, really useful because a lot of times I need to practice writing or test writing to files and loading from files, and it lets you create a temporary directory where you can do that, and then it deletes the directory.
Oh, nice. I hadn't heard of that one, but it sounds great.
Oh, it saves me because otherwise you have to make a dummy directory, and then you have to try to delete it, and then if the test fails, then you have a messed up folder, and then you have to put it in, and it just handles everything for you in your temporary directory on your computer, and then delete them. That's my favorite fixture.
that was really good. Honestly, I've only ever used the ones for the randomness, but yeah, talk to everyone. I'm sure people are using cool stuff. Okay, are you ready for CI? Cool. Okay, so collaborative development without CI usually looks something like this. So you have your machine and your colleague's machine, and what you're doing is you're both kind of developing, you're running tests, of course, and then you're committing to your local Git, which then is connected to some remote Git, which could be GitLab or whatever you have using, and then you know, the other guy is also doing the same thing, and you're both committing to the same code base. And essentially, this is where the work kind of comes together. But now, what if you're running Windows 10 and I'm running Ubuntu? And then you tell me, yeah, but your code doesn't work, but I go, well, it works on my machine. And then you have reached an impasse, and at some point your professor is going to come hit you because the code doesn't work. Yeah, there needs to be some kind of infrastructure that allows you to make sure that this stuff, that your code works on all kinds of different versions and operating systems and dependencies. And also, if you're working with compiled code, this is a whole other thing. So I hope I've convinced you that there's some point to creating some infrastructure that will do this. So continuous integration is essentially that infrastructure. So it's a set of tools that helps you make sure that the collaboration project works smoothly. It can also be used if you're really just by yourself. Honestly, also useful because you can make sure that people who are using your code, or maybe people who are using your code in the future, which might be you, would still be able to. It will work on all systems. The idea is that there's a lot of stuff that we can in this that we can automate. So these are some of the examples of things that we might want to automate. So make sure the tests always pass, check for the style, give you an error when there's a colon missing after your function definition. And yeah, so that's CI. And the way that it often works is that you have a separate server that does these jobs. So it's essentially, we can create a virtual machine, which is a minimal version of an operating system that can run on here. You can decide what packages there should be, which OS it should be, which Python version it uses. So you can create a clean environment for your code to run in. And then that thing will run your tests, it will run your linting and style checks, whatever that might be, your code coverage, any kind of tasks that you might want to perform. So what would that be, for example? Well, for example, if there was a pull request or a commit that is pushed to the master branch, then or the make branch, run all tests for all the different kinds of versions. Maybe you define that you want your code to work from everything from 3.5 onwards, and you define various kinds of versions that verify that this runs. Another, so usually the structure of it is that you kind of define a trigger. So for example, there's a commit, and then the tasks that run. So another potential trigger would be a version bump. So if you're actually writing software, and then since you can design versions, and then there's going to be a trigger when the version goes on. Or alternatively, when there's a tag added to your there's various infrastructures that help you do this. We're going to talk about GitHub Actions. If you're using GitLab instead, the structure is going to be vaguely similar, but yeah, we're going to be using GitHub Actions because, nicely enough, in GitHub, you don't have to have a separate server that does your CI stuff. It kind of allows you to use GitHub Actions as an interface between your code repo and your CI tasks. And it does that through a file. So there's a hidden file inside your Git repo. You can make a folder called .github/workflows with another directory, and then GitHub Actions YAML file, and that's where you're going to write these triggers and tasks into. And this next section, it's I don't know. I hope the word boilerplate rings a bell. So boilerplate code is the stuff that you do. You take it, you copy paste it, and you change the options you want. Nobody will ever expect you to write a GitHub Actions YAML file without looking at a reference. So this sort of stuff is always going to be done by kind of looking at what does this configuration pattern to look like, and then copying it and then changing things. So yeah, for this, don't get don't be afraid of these like really long weird looking files. So the idea is that there's an action trigger that you define. Every time anything happens, GitHub checks whether in your workflows in this config file, whether there is anything that it needs to do, and if there is, then it creates a virtual machine, just as you specified in the config file, and then runs. And I don't know if any of you have ever committed anything to a larger project. Has anyone ever contributed to something like sci-fi or even something smaller? No one? A little bit? Okay. So if you have, then this is going to look a bit familiar. So if you do a pull request somewhere that has that's a big project that has a big infrastructure, they always have a CI pipeline because NumPy needs to make sure that whatever you're pushing isn't breaking all of NumPy. So they have a lot of very specific checks, and so as soon as you make a pull request, it runs all those things, and then it gives you this report, and it says, all checks are passed, or else this thing failed. Please fix it before asking us to merge. So yeah, this is kind of what it looks like. And then on the GitHub Actions, so in GitHub, you can, I know that this flag has changes, but in GitHub, there's one of these little cards at the top. It's called Actions, and this is where you can also see whether your workflow ran or not, and then you can click on it. But this is all at a very abstract level, and I think we can continue to just looking at what this would look like. And like I said, I think we're really just going to copy these. We're not going to write them from scratch. The hope was, or the idea was, for for this last section, was that you have this testing project repo, and there are some tests inside, and some of them run, I hope. Even if they don't, you can do this all the same. In that repo, you will now add this file. So when you make a directory called GitHub, you make a directory inside called workflows, and in that you make a file. It's called config minus name. Anything. So you can give your workflow name. Config minus anything .yml, and then you write us a little file of this structure. And this is essentially the little explanation. So on is the trigger. So push or pull request, for example, would be an example. You can also do something like tag. But like I said, we would need to look up what the exact names for the triggers are. Then you tell it you want it to run on maybe Ubuntu. And then this is essentially the steps that it should take. So first of all, it should set up a Python environment with the following Python versions. It should install some dependencies like PyTest and Numpy. And then lastly, the last one of these steps would be to go to run your testing command. So this is PyTest minus SE, and then this is our testing folder that we were using, but it's going to be something different for you. And here's where you can find more about all the triggers and the actions of this. But so the idea is that you try this now. So make this folder, make this file, look at these references to, or this reference. I'll keep this up if you want, to write the YAML file, and then commit to enter the changes. I hope you fork your folder, and then you can push to your fork, and then once you have pushed your workflow to your repo, then you can look on GitHub. Then you can go on GitHub. So, for example, into your repo, and then you would go and find this Actions tab here, and once you have added it, then you're going to get your report. So, if you want to do copies, so I mean, it's here. The contents of the file is here. Yeah. You can also which so the PDF of this presentation is in the repo. But you can also just type this out. It's not so much more to type it out either.
Right now, and then it will take all of it. So all of those. Probably the way I told oh, wait, actually, found.
We're just a man. We use this.
Yeah. I use GitLab in my work, so I know. Yeah. That's fun.
Sorry, do you want to create one now?
Want to see?
Are you ready?
One thing, everyone, these are not tabs. These things, they are not tabs. They are spaces. You cannot use tabs. I'm sorry. I should have said this, but it turns out that in YAML files, tabs are forbidden. So I was using in this file, I was using 2, but I think 4 should work. The recommended number of spaces is 2. So yeah, this doesn't require people to have any. There should be some information All right. We're gonna finish up. I'm just gonna quickly show me doing it. And then if you want to keep playing with it later on, feel free to do so. There's also some more complex configurations in the further side if you want to check it out. But so I have my folder here. I made a folder called GitHub. I made a folder called workflows. So folder.github workflows, and I'm just gonna take this stuff. I have the luxury of copy pasting, and copy paste this into a file here, and I'm gonna save it. Where's my folder?
That should make it press or command. No, command shift. No.
Good point. Okay. And then I'm gonna call it. Okay, and then the other thing I need to change is that this is not relevant for us here. Just running higher. So that should be fine. And then I'll go into that. I have a bunch of uncommitted stuff, but I don't care. Where am I actually? So I'm going to just push this straight into our so git and GitHub.
And maybe also the best.
Yep, and then so now I've added these things. This I should not have actually added, but I'm just going to ignore that for now. So we've added them. We're committing them. Upload and then push. Set my upstream. Sorry. And I have a mess. That's just great.
Do it standards.
Okay.
Right, so if we so now if we go on actions, we see that we have our we had one workflow run, and it's called run tests, and it seems like it all passed. And then you can kind of see all the different things that it went through. So it's set up Python and installed all the dependencies, it tested the stuff. You can look at all the output here and configure it. You see that it's passed. Good job. So yeah, this is how it's supposed to look, minus the merge conflict. I don't know how that happened. So yeah. So CI, it takes a little bit of work to set it up. It's also very fiddly. Like you have tabs instead of spaces, and then it will complain, and then will take a little bit of internal strength to put up with this kind of complaining. But once you have set it up, it's really useful because every time you just, at the end of the day, you push your changes, and then you have some confidence that what you did, well, either you need to work on it tomorrow because there's really a problem, or you know that your problem. So yeah, this is the end of the CI part, and also the end of the testing lecture. But Pietro had something to say?
No, just so I just wanted to give a quick pointer. So if you're interested in following up on this kind of topic, so it's good practices and testing and a little bit going a little bit more. I know that it's not fashionable anymore to read books, especially about programming, but I can more really recommend these. They're going to be short in a minute. They're not necessarily about Python. They're not necessarily about Python, and you might find some Java stuff or some other programming language. But it doesn't really matter, right? It's really about the practice of programming. This book is about test-driven development, so this idea of writing a test before you write the code. So yeah, which is nothing. And then there is more. Is you want to how you talk about programming? So thank you and enjoy the coffee break.
So what is ready now? 15 minutes. So we are back 24. 10 minutes later.
All right.
I would say,
Yeah.
we should do big numbers.
Yeah, there's no video that can.
Sí.
Yeah.
Okay, because now I mean like just. So maybe one way is very likely. Because the issue is not one option. And then there's control for the and you have like up Yes. And we're trying figure out the name from the test.
But in right you'll know the number.
Yeah.
I don't know if you think about
No, I think the general purpose, I think it's okay, but then, you know, like. Some of the. Just, should be more of the. And if it doesn't, then it would be nice. Okay.
The rest?
First part.
So if you have size,
So, you have to say that think about something. Yeah, so there's a problem between doing the whole class and just some but then it seems you have to develop speed. And at the same time, learn about
I don't know, I mean, I agree that the case where you're writing a problem from.
the beginning is the size of the first part or was it part? And there are situations that you can.
Yes, 100% of the brains.
Another the same. There's a thing, right? And then the advice. I mean, my point is that it's unnecessary to go. That's about testing. And so I think it's distracting, but then yeah, that's right.
Then you can put. Exactly, following this, right, like something like that.
Yeah, there is a title, but normally the meeting is. And, yeah, I mean, because, yeah, I mean, people are out there, you do it with product. So now it's faster at that reason.
Yeah, there is a special.
Yeah. I kind of agree. There was this, I mean, there is a more link. Yeah, I think.
Yeah, that's not necessarily what we do with them.
Yeah. I think it's a good point to add, you know, doesn't mean tomorrow. So the idea of giving you both the function and because in the actual examples, it depends on the yeah.
I don't understand, but it's still like a blind function.
Yeah. Yeah, that's quite a lot. As industry did not
Yes, of course. Yes. Yes. I think this is not it may be if it's
Yeah. If organizing is not the
Okay.
Where's the eraser?
It was inside that.
Okay. Yes,
yeah. It sounds crazy because
Stars again?
Switch partners, please.
Just like yesterday, try to find somebody new.
Hi guys, welcome to new lecture. The lectures today are going to be Guillermo, Seetha, and myself. And we first want to thank Aina and Lisa, who were teaching about this lecture. And then there are material and all effort taking advantage of that. Okay. I will see it because we have some departments regarding coding. First, the name of the lecture. Oh, sorry. And also might be a bit pretentious, so almost advanced. Good. First of all, just a little reminder about what Numpy is. I guess it's warming up. We have Numpy basically to work with arrays. We have, for instance, 1D arrays, like array, and then this. Okay. This is a list with integers inside, having if I put a dot there. One of the numbers is not an integer anymore, it's a float. What's going to happen? All of them are going to be a float. Okay? So we cannot mix types inside. There is a function to make an array with zeros. Yeah. And without 0, you can specify the amount. But this is by default float. Okay. We can make also an array. Once you can get a name, right? Okay, also floats. Good. More on the arrays. We can make a sequence of arrays. Good.
I think it's big. This one, the beginning, the steps and the
Yeah. What do you mean by sequence of arrays?
A sequence of numbers. We put this. We get a sequence with 10 numbers. Okay. Information about the hint about the arrange function. You can specify a starting point, a stopping point, and a step. And by default, your start is 0 and the step is 1. That's why before we only use one argument. Okay. So how can we get the same sequence but reversed? Okay, the step is going to be -1. I will put first the step if you want.
Zero, 10, like
Sorry, let me say
step 0, step 10, the step.
Step 0, step 10. Like this. What was the question again? Sorry. I want to get the same sequence, but yeah, this column, 1 1. No, you need to specify the start, the stop, and the step.
That is not on.
Who is happy with that? Yeah, the first point, the first number is going to be used. So I cannot start in 10. I have to start in 9. What happens if I finish in 0? Yeah. Usually this usually happens in Python. Okay, the first number is taken and the second number is not. The reason is that when you use only one single value here, the length is exactly that. Okay, so here, what should I do here? Let's see. Oh, I'm Spanish. I use two M's. Works. I can also generate some random numbers. For instance, oops, sorry. It's a module called random. And inside, for instance, I have a random function. And I can just specify, for instance, number from 0, 10, and how many. Okay? For instance, 10. Okay, 0 is included or could be included, 10 is not going to be included. So I get the random numbers function 9 and also 10 as previously. We can also use to the arrays. Guess what? The same function as before. Zeros. And now we can specify, for instance, 2 times 10. And we get 2 rows, 10 columns. Here with sums, okay? Equal, expected. The same with ones. Lazy. Lazy but slow. Get also ones, okay? We can also get a random number. I will random again, specify also again what I want to times 10. Make it another right, 97. What happens here? What should I do?
Use it.
What is missing here? What we did before. We provide the options. So if I want same numbers I was using before. Okay. Sometimes it's tricky to know which values come by default and which values cannot by default, and when you need to specify something. Well, documentation is not that bad. It could be better. We can also get sequences to the array. Okay. For instance, how can I make it? I want a sequence to the array from 0 to 19 in 2 rows. So from 0 to 9, good. No, that's okay. That's really my lecture. I have to spend a lot of time here. Very fast, okay? I need more answers first, or at least I don't know. Okay. Good. Arrange. I want 20 numbers, but it's really clear. If I do this, I know for sure that the amount of numbers is going to be correct, but if I do this, I get single, all right? Okay, then in the shape, and now I'm pretty sure that it will be possible to get this shape, right? Because the amount of numbers should be what I was saying. Open mesh grids. It gets hard. Which is a function for open mesh grids, you know?
What is the mesh grid?
We'll see now, okay? Let's see the output, then we comment on function for green. So in this, these are two arrays. One is like a column array, and the other one is like a row array. Okay. Usually we save them with this. There's a reason for that. We get X this way, we get Y this way, it's okay. I will just leave it as it was. But what do I get with this? It's just for getting masks. Imagine you have a picture and you want to get a square to this picture. Okay? With this, you are telling that you want a rectangle taking row 0 and row 1, and taking columns from 0 to 8. Okay? I will do it. Let me change all the stuff. Okay? I will just cut this here. Okay, and then here we get matrix. I don't know. And I want numbers from 0 to 100 here, and I want a shape that is 10 times 10. Okay. But if this, look at this matrix. Okay. I will do this, putting 1 here and 3 here, and also here 4 and 7. Okay. What do I get with that? Row number 1 and 2, and columns number 4, 5, and 6. So if I get row number 1 and 2, they are these 2 rows, and columns 4, 5, 6, 0, 1, 2, 3, 4, 5, 6. I should get this square here, 3, 41, 24, 75. Okay? So what happens if I do M, and I only get X, Y, equal. Okay, the square is okay. Right? Good. I will make space because I need space for the next one to appear. That is the other type of mesh bricks I can get, the dense one, that is more logical. It's using MP from brick. I use the same as before, 0 to 2, and then 0 to 9. That was the same as before. What I get is 2 rows with 0s and 1s, and 9 columns with numbers from 0. Okay. It seems more intuitive. Okay. This is good. The other one is pretty useful to get really masks with the square. Okay. We'll see later how to make it more fancy. Good. We also know lists. A list is a collection of things. For instance, an integer, string, float, a tuple. Okay. What happens in this case? The amount of memory you need to store each of these elements is different. Okay. And in this case, when you get a list, You get this. You have reserved a certain amount of memory for each of the elements. Okay. Some memory for the integrals, some memory for the strings, some memory for the float, and some memory. Okay. And the amount is different. What happened with the Numpy arrays? With the Numpy arrays, since all the elements are of the same type, the way the memory is taken is homogeneous. Good. Indexing, we know how to make simple indexing, just using lists, semicolon, and the position you want. So beginning to count in 0 with Python, so it's position 0, 1, 2, and 3. Get through to the list. Now that. Well, this is a list comprehension. I assume you are familiar with these comprehensions in Python. Okay. It's pretty readable. Sometimes it's hard to write, but it's pretty readable. Okay. Like we're taking I when I goes from 0 to 9, not include 9. Good. With Numpy arrays, you can do exactly the same. In the same way. Okay. Then, why use the arrays? I mean, at least I can put whatever I want. At least I can put lists. Inside a list, I can put dictionaries. Inside a list, I can put whatever I want. So why use the arrays? Well, speed. It's really important. Speed matters, and we will compare. We'll compare one function in math package, function square root. Since the function in the math package is only usable with one single value, we'll make a list comprehension, calling that function inside a list comprehension. There is a square root of a whole list. And then we'll do the same with the universal function square root from Numpy that can take directly the array and apply it to each element of the array directly. Okay. The result is going to be the same, and we'll compare the time. Okay. First, let's have a look at the code. Okay. We have a list of numbers, 0 to 8, for instance. Okay. So we're going to make 9 times the square root, each of the numbers, 1 time. And here, what we do is we'll use the function timeIt, calling square root for math. Since it's super fast, I will do it billion times. Okay. Then we have to wait a little bit, and then we can do something. And also, we will sum the time it takes, because we're doing here is a list comprehension. You see, it's a list comprehension because we are calculating this square root and timing it for each number in the list. Okay, and then I have to sum up all the time. So that's the time it takes to calculate the whole list. Okay. Too fast. Hopefully the other one is faster. Okay, 1 second. I cannot do that fast. I need at least 1 second. Okay, so it's a little bit over 1 second. The other one, the same. We make a Numpy array with the list we have before, so we have an array with the same numbers. Okay, and we call the timeIt function, but this time directly calling the function Numpy square root, the function that can take directly the array. Okay, and we're doing it also. I'm not cheating. Okay? So you can count the zeros. Okay. That was close. But it was fast. I mean, both functions are fast. But it was fast. Imagine you have to do much more complicated operations plenty of times, so in the end.
Here it was faster for the list.
Yeah. You're wrong. It never happened to me, but I was worried.
Already 2 times.
Okay. The thing is that the difference is so low that anything can make it if your computer is doing whatever, changing whatever is behind, then it's good. I would take the risk of doing it again here, okay? No. In my case, it seems to be stable. Yeah, it's stable. Okay, I can check again the other one if you don't trust me. Hopefully it lasts longer than a second. Your computer is wrong. Okay. Good. So we are done with this part, first part. So this was a little bit of a warm up. Do you have any questions? I think with the time, we have. There is another session on high performance Python. I think people know more about timing issues than us. Maybe then we can leave it for them. This kind of change. Yeah. So everybody is on everything what we said before. So everything what we saw already, everybody knows it. Right? Or remind. So one thing that you may not know, or maybe that you just use it just now. You know probably normal indexing, so one number, or you know how to do a slice. So imagine that you have this already. And to get a single element, as we just saw it, you will do something like that. So to get the second, that will be the second row, right? To get the second and the third, you will do something like that, right? So, and that's what is called a slice. It's not part. So one is regular indexing, the other is a slice. Now, there is another thing that is called fancy indexing. That's why the name. And fancy indexing, you can do it. So there's another way of indexing where you pass in the arguments as you pass multiple lists, and these are interpreted as coordinates. So imagine that from the same array, you want the first row, second column. So you want this row, second column, the 1, and you want the second row, third column, the 5. So you could do it because these are in different rows and different columns. You can fancy indexing in this way. The first element would be the first in the first row, and for the second element would be in the second row. And the first element, the columns, will be the second column and the third column. So what I'm passing here, you see 1 and 5. What I'm passing here, maybe I'm passing this to lists where these are interpreted as kind of coordinates to look on the row dimension, and these are coordinates to look at their column dimension. And it will return here. Will return an array of 2 elements because each of these lists has two elements. This could be fun. So this way of indexing is called fancy indexing. And you can do, so you can, as what the example Carlos at the beginning with X and Y, the whole grid, that was actually fancy indexing. He passed X and Y. So another example, maybe a bit more complicated. So imagine that you have that array. So you have possible the letters of the alphabet, and now imagine that you want to print, oh my god, you can fancy index it and say, I want the O is in the second row, right? So the M is also in the second row, and the G is in the first row. That would be the X coordinates, and the Y coordinates would be O is in the second column, M is in the first column, and the G is also in the first column. Yeah? Good. So, visually, just to completion here. So this is nice visualization from Lisa.
if you think about this, you know, what we did here was to say, okay, what are the row indices? 2 to 1, 2 to 1, and the column indices was 2 to 0, 2, 0, 0, and I get, oh my god. But if I now pass, if I want to have this, oh my god, and wow, at the same time, I could do. So I can actually do this. So I can make a matrix to an array with only the rows, and then an array with only the columns, as it is here. So 2 to 1, 3 to 3 for the rows, and 2, 0, 0, 4 to 4 for the columns. And now if I fancy index an index as it is here, you see that I get an array with with that is 2 by 3 with the elements that I wanted from the indices that I chose. Is that clear? A bit you have to wrap your head around that. But this way of
Does it need to be arrays? Because previously
you can use list or arrays. Exactly. You can use list or arrays. So this is something that maybe is not so known about Numpy, but it's used in connection with, for example, algorithm, where you pass as the index, you pass an array. So related to that is that so we can combine two things. That was fancy indexing. Now we can combine with what we saw before, with slicing with index, regular index. So for example, again in the example of the alphabet, C, A, and B, so cap is in the same row. So I could also do, I could also do 0, because that's in the first row. And now give the coordinates of C first, which is C2, 1, 0, 0, and 1. Right? So one can also combine this. And now even more combined, so you can do, imagine I want just a slide, I want a part of this array, where I want the first and the third row. I want the first and the third row. And I want the last column and the first column. Does that make sense? So the first two rows, right? And the first, I want the last column, so F, L, and R, and then A, G, M. And that's what I get. And the -1 is an index of the last element. It's also so, is that clear? Yeah. And that related to that, what I'm going to say now is that Boolean arrays look like you can also index passing a Boolean array. So imagine that you have this shape, so you have this array, and now you want to only select the values that are higher than 5, or higher than. So what you could do is to say, so I can say this is my array A, and then everything is as greater than equal than 5. That's a Boolean array. Right? This I can save it. And now if I do A with index I, which I was that Boolean array, then I get only the values that had that condition. And this is also fancy indexing because I is an array that I'm passing as an array. Okay. So this I did already. This I will skip because time. So now the fancy indexing, so this is useful, and it's even more useful to know that if you do this kind of fancy indexing, you are imagining that the array is in memory, and now you're looking at different portions of this array. What Python is doing in the background, so Numpy is doing in the background, is actually doing a copy of the array. So it's taking these values and putting somewhere else in the memory. And an important distinction in Numpy when you work with arrays to know if the array is a view or is a copy. This is what we're going to talk about now. So a view, when you do a slice, when you do a regular index, it's a part of the buffer of the memory that is allocated, and you have direct access to that memory. A copy, for example, by fancy indexing, creates a copy, and it doesn't. So if you change something in the copy, then it will not be reflected on the original. So we will do an example. So imagine now I have this 1 to 6. So this array. Now, if I do a slice, for example, 0 to 1, no, 0 to something, 3 to 4. If I assign this to a new variable, right? This I took a slice, and this is 3 to the third and the fourth element, so it will be 4 and 5. The fourth and the fifth element, the fourth and the fifth element, sorry. So, but if you now b dot, if I now do b, and I assign to the first element, I assign the number 10. And now I print b. So it's true. I just slice this array. A is 1, 2, 3, 4, 5. The slice is 4, 5. Right. And now I change the first element to be 10, and now it's 10, 5. But now if I print A is also changed. You realize that? Why is that? Is because B, I created B using a slice, using a slicing operation. And the slicing operation is giving me a view of the array. And it's the same thing. It's not, the data is not copied. So be careful. So this is what you want to know if this is a view or this is a copy. If I will do, did you know about this? No. Yeah. So if I do now, instead of that, if I do A, and then I want a third and the fourth. So if I do now this is fancy indexing. Because I pass a list for the array. I edited, I did exactly the same thing, but now the original array is not affected. So it's important to know that these two things. So when you're doing a slice or regular indexing, to compute, and when you are fancy indexing, or the alternative will be to do a copy, force a copy, and this you can do it like that. So you can do a copy. If you do that, then you are forcing a copy of the array. All right. So we're gonna go into the exercise immediately. So this is just the same thing. Like the take-home message here is that you do need to know if you're using a Bureau copy, because you could be operating on different things. You could be operating in an array that you want to change stuff. So you do need to know to have Bureau copy, and we'll do an exercise now on that. Okay? And the last thing that for this kind of the theoretical part is just sorting, because we're going to do sorting. Yeah.
When you, instead of doing slides, you just access one element via its index from the list.
That's also a view.
That's also a view?
Yes. So coming back. So here. So regular indexing, that would be the normal index, or slicing gives you. And fancy indexing gives up. And that has to do with the memory behind it. So in fancy indexing, you need to look at the memory at different places, and Python cannot do it just by looking at the memory. It uses kind of. And I forgot, so you can always know here. So if here E is a copy, so you can also print. So the arrays have a an attribute that is called base. So I will comment it. B.base. When the array is a view, the B.base will return you the base array. What's the father or the mother array? And when you do a copy, then it returns none. That's always a nice way to check this. So when it doesn't when it returns something, it means that it's a view. And the last thing is sorting. So when you use it in the exercise, is that you probably know this, and sorts an array. And here, for example, this is an example of a function that can be applied, can return a copy. So if you do mp.sort of an array, whatever array, this S will be a copy. But if you do .sort of the array, they will change the array will change in place. Right? So yeah. And that's no. And the other thing that you may know, so flip can sort change the order of numbers. So you can and arg sort returns you the arguments.
But this sort is a view or
which one?
The sort. You sort.
So if you do this is a copy because it returns with the array sorted. Returns the same array but not sorted. And that would be a copy. Yeah, and then arg sort, which is the last thing to do, is so imagine that now you want to sort, but so I will comment this. So this is an array that is a random array. So between numbers between 1 and 50. Now with arg sort, I get the indices that I need to sort the array. I don't get the array sorted, I get the indices that I need to pass to sort the array, which can be useful sometimes. So then afterwards, I can pass this I, the indices, as argument, as indexing, and this is again pass indexing, and it will return the array sort. So I is the indices, and this will be the same array as before, but just sorted. All right, so the first part of this section, if you go here, we have exercises on indexing. So different types of indexing and the shape of the dimensionality of the Numpy array. You have to also know if it's a try to answer if it's a view or a copy what you're doing with the indexing. And and you have to sort an array. The first exercise is discuss with your partner if it's what's the dimensionality of the output, how many rows and columns, because all the indexings are sometimes very confusing with the numbers. And if it's a view or trouble, that's kind of straightforward. This part exercise. The main exercise here is that we try to recreate the indexing of these matrices. So everything that is in yellow, imagine that this is a matrix of 11 times 11. And you only want the values in yellow from the matrix. So by indexing in different ways, you have to get this one out. And there is a function here to visualize. Right? So that's exercise 1. You can let's start. With the partner. It's better than discuss yourself. Espera la llegada pasada, espera la llegada pasada. So what does it mean? Right. So remember, so usually start and stop step, right? But if you only want to provide a step and the start and stop is default, you have to put this column. So this start, stop, this is all of them, but every other. So, okay. Continue. There were other questions about this. Start, stop, yeah. Okay. I wanted to just answer to everybody a question that has come about 1.4. If you find it complicated. So, yeah, because it's a bit unintuitive, and I wanted to show you here why with a smaller. So you have A here, which is I did it smaller, so it's 3 by 3 by 3. It's the numbers from 0 to 26. B will take this form. So with the fancy indexing, that form. And you may be surprised when you execute it, and you saw that B.shape was 2 and 5. In this case, it's 2 and 3. So if I do this, fancy indexing, I get an array that is 2 times 2 by 3. Do you know why? So you would think that this would give you an array of 2 times 2. No? So it will give you the this maybe I can explain to you here. Imagine that the array is only two-dimensional first. No? It's only two-dimensional. So it has 3 and 3. 3. It's that 4. Okay. So like this. So the fancy, if it would be only two-dimensional, the fancy index in there will take the second row and the second column. So this element, right? We will put it here. Yeah. And the second, the third row and the third element. This one, and it will take this one. Yeah. And it will return me this array, right? But now the array that we have is 3-dimensional. So it has another dimension here, it's a cube, and I'm not specifying the dimension in the indexing. So by default, Numpy takes all of the elements. So imagine that this will be like this, but now in 3 dimensions, in the next dimension. And that's why it's 2 times 3 in this case. Yeah? So that was kind of the that was unexpected. Now, did somebody manage to arrive here? Yeah, so let me just wrap up because we have to continue a little bit. So this was just this decentralized exercises of indexing, and I think I hope you can wrap your head around how the different ways of indexing work, which is complicated, and the views and copies thing. No? If you do try to assign values to the view, it will change the base array. That's the main point that I want to get out of this. So now, there is more in this notebook. So now, as our previous student, also said, you can go home and continue exploring because you can finish here. There's a fun exercise. So this is just a fun exercise of doing. So everything is in solutions, by the way. So all the solutions are in the folder solution. And afterwards, you have, after that, you hear the solutions, you can have a look. And you can also create something like this, a circular mask. Yeah. So this is also useful sometimes to just get the cellular of an image or something. So, but now we need to touch another topic, which is broadcasting, which is related to the topic that we just saw. So now we go to broadcasting, and then we have another exercise on broadcasting. And this part you do it.
All right, ready to switch gears a little bit? Not hard, but okay. So has anybody heard of this term broadcasting? Has anybody heard this term broadcasting before? Okay. So I'm going to add these two arrays. Okay. Has anybody seen this error before? Lots of nods. Yes. Anybody never seen this error? Okay. So you always get this error, right? So it says operands could not be broadcast together. Do you know why it says that? It's got different shapes. So one is 2 and one is 2 by 3. Right? Okay. So let me do something here. That's fine. Okay, what do you think would happen? Would I get an error? How many people say yes? I get an error. Raise your hands. Don't be shy.
Who think you will not get an error?
Who thinks I won't get an error? Okay. So the rest think I will get an error, right? It's a binary. It's yes or no. There's also I don't know. But I'm asking you if I'm putting it yes or no. Okay. Everybody says yes, I'll get an error. There's 2 people who say no. I did not get an error. Okay. So this entire lecture is going to be about this. Why did I get an error in the first case, and why did I not get an error? Okay. And it has all to do with this thing called broadcasting. And I am going to try and control shift minus.
Yeah. Okay, minus.
Okay. Good. So broadcasting is basically this term that's being used in Numpy, but it's nothing to be afraid of. It's just a term that describes how Numpy treats any array that you give it and how it's going to perform mathematical operations on it. Okay? So we've talked a lot about the Numpy array today, and we already know about like that there are different kinds of array, different shapes of array, different dimensions of array, right? So say if I had an array, a 3 by 3 array like this, it's got a lot of properties, and I'm going to print the properties here. And you can kind of see that there's this property called size, which gives me how many elements are in the array. That's 9. How many dimensions, and dim, it's 2-dimensional array. And then the shape, that's 3 by 3, and the data type. So for broadcasting, we're really just going to mostly focus on understanding shapes and the dimensions of the array. So let me start by just taking you through like how array operations are done in Numpy. So you can imagine that when you give Numpy 2 arrays of the same size, and you say add these, it's going to add them element by element. Kind of what looks like this. So if I have an array, can everybody see? Yeah. Okay. So if an array like this, and I say 5, Okay, so it's going to just add element by element, and I'm going to get the result here, which is 0 and 1 added to 3, 4, 5, 6, 7. Okay, that's an array of the same stuff. But interestingly, I can also do this where I can add a scalar to this vector x. I can do this, and it will take this tree and add to each element of x, even though they're not the same shape. Okay? And then what I'm trying to tell you here is that I don't have to do these things in order to add 3 to this array x. I don't have to loop through x and add 3 to each element. And I don't have to create a set of trees that's the same shape as x and then add them together, which you probably do in some other languages. And of course, it's an inefficient way, right? You're creating a new copy, you're creating 4 loops, it's very inefficient. And the awesome thing about Numpy is that you don't have to do, you just say x+3 and voila, you get everything added. Okay. So obviously, when I do those things, I get the same answer. So that's what we think of broadcasting as this extra step that happens where that tree gets stretched to tree, but it's not actually happening. It's just the model that you think of in your head that should happen. It automatically happens in Numpy. And it's obviously more efficient and involves less memory, as I told you. And yeah, so this is just a pictorial representation of that. So, you know, we have 3, it kind of got stretched into 3, and it automatically got added without actually having to actually do those steps. So we can think of it in the 2D way as well. So say I have these 2 arrays. So one of them is 1-dimensional, another is 2-dimensional. And the cool part is that in order to add this array A to each row of B, all I have to do is A plus B. 1, 2, 3 got added to each row of B. Cool. And I don't have to do it this inefficient way. Okay, anyway. So I don't have to do it this inefficient way where I have to use a math function, or I'm just trying to teach MATLAB because I had to use it so many times and it's annoying. Anyway, so I don't have to loop. I don't have to create these repeated intermediate arrays with that too, and I can just do just A plus B. And that's kind of what is represented here too, just like I showed you with that scalar and vector. So I have this array, and then I have this 2D array, and this kind of just got repeated automatically and got added to it. Okay. So that's what Numpy broadcasting is all about. And when I say this, it's not like it's physically happening somewhere. It's just happens. And this is just when you think of broadcasting, you're just thinking of this mental model in our head. Because we want to understand if we add A plus B together, what's the results, right? Why am I getting a broadcasting error? What went wrong? And that's really why we are trying to teach you broadcasting here today. One of them is that it's easy, like I told you, efficient. You don't have to write loops, so you're adding things together. But once you understand it, you're also going to be understanding those broadcasting errors that we saw, and why one shape worked and the other shape. Okay. So I'm going to start by saying what happens during broadcasting of 2 arrays. And it's really just boils down to 3 loops. There's a lot of words here, don't read it number 1. I have boiled them all down to these 3 words. Okay, add, stretch, check. And we're going to come back to this again and again during the lecture. So just remember, add, stretch, check. Okay? And we go through each of these rules. 3 rules. Add, stretch, check. So what happens? Okay. Let's start with an example. Okay, so we have these 2 arrays. Anytime you're adding arrays and you get errors, rule of thumb, print their shapes. Okay? Print their shapes. So I'm gonna print this shape here. And maybe what I'll do is do this on the board, it might be easier. Can everybody see this board clearly? Anybody who cannot? Anybody over there who cannot? Okay. Can't see it? If I write on top?
Maybe.
Maybe. Okay, I'll try. Oh,
No,
no. Oh, this yellow t-shirt.
you feel like it looks like.
Takes off his head.
You're right.
Just take off your head.
Okay, yeah.
Okay, all right. So we said add, stretch, and then check, right? Okay, so I'm gonna not focus on the array itself, but I'm gonna focus on the shape of the array. Okay, first, so we have A, which is a one-dimensional tree array. Okay, three columns, and then B is basically a 2x3 array. Okay, so rule number 1. Okay, rule number 1 says if the two arrays differ in the number of dimensions, the shape of the one with fewer dimensions is padded with ones on its left side. Okay, let's break that down first. Okay, so now we're first comparing dimensions. 1D array, right? 2D array. Got it? Two arrays differ in their number of dimensions. They differ? Yes. The shape of the one with fewer dimensions, which is A, gets padded with ones on its left side. So what that does to A is it makes its shape 1x3. Okay? Rule number 1. So shape of the array becomes 1x3 because they have smaller dimensions. Rule number 2, stretch. If the shape of the two arrays does not match in any dimensions, the array with shape equal to 1 in that dimension is stretched or broadcast to match the shape. Let's break that down again. If the shape of the two arrays does not match any dimension. So this is a 2x3 array, B. A is a 1x3 array. Shape does not match in the first dimension. Okay? So now A is going to get, and then A also is 1, right? The first dimension. So the shape equal to 1 is stretched. So what do we get now? A becomes 2x3. Okay, so A is stretched to match the dimension of B, which is 2. Now you have an array of shape 2x3 and 2x3. Okay, so that's what we saw. And then, so now you check if the sizes agree, add them together. What's our expected shape of A plus B? A plus B. 2x3. Okay, so does that make sense in your head how broadcasting works? Okay, let's check another one. Same way. Okay. This time. Okay, we have A is 5x4. B is 4. Anybody tell me what's happened in the first step? Yes.
B changes from 4 to 1, 4.
Okay, good. And then next, stretch.
It changes from 1, 4 to 5, 4.
Easy. Okay, so now you have A and B. Good. All right. So we get the shape. 5x4. All right, one more. Okay, what did I do here? So I created two arrays. Has anybody used new access before? Okay. So what new access does is, so let's see. First, it doesn't have a- There we go. So if I had this, I'm just going to copy array into another variable, so I don't have to. Okay, so that's this array, right? So now if I do np access, what it does is adds a new access to that array. So now if I were to first and then looks like that. Okay, so it looks like that now. Okay, does that make sense? So it's kind of broadcasting, but not on the left side, the right side, but you can do it on the left side too. So if I were to do it this way, okay, then I'll get a 1 by 2. Okay, so it's just a nice way to add an access to your array. So that's what I did here. So therefore, I got an array A of shape 2 by 1, and B is 2 by 3. Okay, had not the same person, and not someone else. Nothing happens in pad, right? Nothing happens in pad. Because you have the same dimension, stretch. Yep. Okay, so check. All good, right? So it works both ways. Left side, right side. As long as you have something that has a dimension 1, you can stretch it. And okay, let's try a bit more difficult. Maybe. I think you guys are pro in broadcasting. Okay, so we have A, B. All right, what happens with pad? Sorry? Left side. 1, 3. So padding always happens on left side. Okay. So B remains the same. Stretch. What? Which one? Okay. But B? B? Same thing. So broadcasting can happen on both arrays, not just one. Okay? So be careful when you add two things together. If it works magically, print the shapes. Okay? So now you get a 4 by 3 array from something that was 1D, 2D, the 4 by 3 array. Okay? All right. I'm not going to bore you with too many. Try this. All right. Okay.
They just
Okay. Then stretch.
change.
Sorry.
Both change.
Both change.
A and
It doesn't change.
A doesn't change. Okay. So I had two options. So A changes to street 3, someone said. And someone said A doesn't change. Okay. And then what happens to B? B stretches to 3, 3. Okay. So let's see what happens. Okay, you understand why that happened? Because A does not have anything that's one-dimensional. So nothing's ever going to fall into A. B, on the other hand, had this padding and then stretching. So that's what happened. So then you didn't check, failed. Understood? All right. So yeah, that's kind of just depicted. So we had the 3 by 2 and then the 3. We padded and stretched it, not compatible. But this was something that someone said that you could do a 3 by 1, right? Then maybe everything would have been fine. Instead of padding B on the left, you pad it on the right, everything would be fine, right? 3 by 2, 3 by 2. You know, we don't try to not have such ambiguity when it comes to rules in programming. So if it says it's going to pad on the left, it's going to always pad on the left. But you can force it to pad on the right if that's what you want. If you want to force these two arrays to combine together, you can do that 3 by 1 and then stretch and everything works. Okay. So what I'm telling you is obviously all not just for addition. You can get one for any new function you want, division, multiplication, whatever you want. Also translate to any number of dimensions. So let's play with this stuff. Okay, I'm doing a 3D array and a 1D array. What's the final shape? Just tell me the final shape. Okay, we can go pad and stretch. That's fine too. Okay. All right. And we have 3. Okay, what happens to B? 1, 1, 3. Stretch. Right? So that's how you can add a 3-dimensional array. 1 dimension. What about this? Beautiful looking thing. Okay, pad step for A and B. Pad A. Nothing for A, okay. B is what? Yeah. Stretch. B. Yep. Get out. All right. Okay, I promise to fill up before you go to exercise. All right, A. Right. Nothing. B. Stretch. Okay, again, only if it's a 1 dimension, you can stretch. Okay, nice thing. All right. Okay. All right. So not compatible, right? Okay. Error. Yep. All right. So you guys are pro at broadcasting now. So a quick recap of what happens, and you're going to put it on exercise. Okay. So you have 3 exercises at the end of your notebook. First one, you're just going to figure out the shape, write down the shape here. And figure out the shape, expected shape, and true. Okay, so make sure you get true. Exercise 2. Again, for all exercise 2 and 3, do not use formulas. Use the power of broadcasting. So you're going to create a random array. You're going to calculate the maximum value of each row of the array, and then you can divide each row like that. Okay. Exercise 3. We have this array called observation, and there's these bunch of values called clusters. So you basically have to find which cluster this observation belongs to. There's a little pause, and I think I should do not as good as Matt, but like I didn't listen to it. I was just in a hurry. But this is the observation, and these are the clusters. It's obvious that this belongs to cluster 2 because it's closest to cluster 2. A little formula that you can figure out, that you can implement to figure out that this observation belongs to cluster. Yeah? Those are your exercises. Let us know if you have any questions. Do you have any questions about broadcasting?
The idea of the exercise that you will be broadcasting.
Yes. No formulas.
No problems. No.
What is it? Well, I just say that one of them is a trick question. Just wanted to let you know, don't get stuck. One of them is good at it, no matter what you do. Well, it's just great to do something. Don't do
So if you finish already, you can stop. We're going to give 5 more minutes and then we're going to wrap up. Okay? 5 more minutes.
Right. So I saw many already finished their exercise 3. Let's go over quickly. So I think many of you already got that part right. So I see. Okay. All right. That's so, and the last one is an error, right? For the exercise 2, here I just print A. So that's my random. Matrix. One, there's a couple of ways of doing this. Huh? Some people I see that they use sort, I think, and they use sort and then they got the last element. That's one way. Another way, maybe more elegant, is to use the max function. And something I admitted I didn't say, but many of the aggregation functions in Numpy, for example, mean, sum, max, min, they have an argument that is called axis. And then you can choose if you operate along which dimension. So axis 0, axis 1, and if you have even one dimension, you can do axis 2, axis 3, and so on. So in this way, you get the maximum, and then you just divide. So because A and B, you see A is 5, 3, and M is 5, then you can do that with the help of broadcasting. So M, you are adding a new dimension to M. So M will be 1, 5. No, sorry. 5, 1, sorry, 5, 1. And then it could be broadcast. And the operation can be done. Yeah. And the last one, exercise 3. So here it is. So this is previous one. So should I go again? So A is the random input, right? M is the maximum. It's a vector that takes the maximum along the dimension of 1.
So you see this, right? This is 8. And then to do the maximum, you get this. So that's 5, 8, 9, 9, 7. Okay? But it's a 5. So it's along columns. But what you want to do is shape it to row so you can divide. Otherwise, you get background again. Yeah. So that's what the new axis is meant to do. Is to make it row.
And you see again that this doesn't need more. Everything is using broadcast. And yeah, and the last one. So the third. So this is the class implementation. I'm trying to read it now. So she defines actually some observations and clusters. This see that observation and cluster, one is a vector of 3 elements, the 2 elements, and the other is a matrix. But because of broadcasting, you can do observations minus clusters. And this will subtract each of them.
Basically doing this
Exactly.
right? Doing it with
One line, right? And then, so I will just print this here so that you see. So this is that matrix, right? Because it got broadcast and then subtract. And now this is squaring each element, right? Then summing, but along the columns, and then taking the square root. So if I print this, then this will be that array. So the distance of each of the clusters. And then I get argmin. So argmin gives you the index, like absorb the index of the ones in the element that will be. Any question? So here you see also the magic of broadcasting here. So that you don't need to repeat. If you know that this is happening with your change, then you can do that. And in terms of code, the clean code is very clean. All right. Just to wrap up now, so as we saw it, I mentioned it before. These notebooks you've used, the solutions of the notebooks are here in the solutions folder. So you have for all of the notebooks that we use today. Just to go back to this. So did you manage to do this one? Some of you? Some of them are easy, some of them are complicated. I just wanted to go over it. So this is only one row and every other column, right? So you can do it like that. So I take all zeros and then I start here. So this is this second row and every other column, as I said. The next one, this one is all rows, every other column. This will be every other row and every other column. This was kind of this is more complicated because this you can do it in two lines. So I do every other row and every other column, but I start one shift one, and then I do the opposite, the reverse. So I start like that, and so that gives you that part. So this was tricky. So this was tricky. And then the last one for these, here there's two options. I would like more this one. I do arrange. So I get the numbers 0 from 0 to 10. And then this, I pass it as fancy indexing. And I set it as 1. So it will be 0, 0, 1, 1, 2, 2, and so on. That's one way. The other way that we started back then is with mgrid. So you can also get the x and the y's, and then set up when these are equal, it's kind of a Boolean indexing. When these are equal, then you can set up. Because here you're getting the rows and columns in the same with mgrid. Yeah, so this is just to wrap up. And the other thing that I wanted to emphasize again about the first topic is that it's really important the views and copies. You realize if you are operating on a view and you do a change, it will change the base array. And this could be very critical for your analysis, if you're analyzing data and you're computing. Very careful there. Yes, and the other thing is that what we've seen here is on GitHub. So,
also.
of course, make sure of course, you can also We did warm-up, we did fancy indexing, use some copies and sorting and broadcasting. There's a little more advanced topics, and actually the reason why there's a viewer as a copy, it lays down on how the data is met in story buffer, and that is the topic of strides. If you didn't see it, but you can see it afterwards if you're interested. It is not good. We do more exercises on doing a circular mask, and after that, there is the topic of strides. This is a very specific thing that we didn't go into detail. For your practical doing Numpy, but if you're interested, you can do very cool stuff by changing the strides. So this you can check it out. And the other thing that we have some miscellaneous here is another notebook where we have two topics that you can check it out afterwards. One is how to load and save arrays from data to a file, which is the .npy files. That's if you save one file, or if you want to save a collection of files, you also have another compressed format for Numpy, and how to load it. That's here. And the other main topic that you may want to be interested in mask arrays. This is something a bit more complicated. Imagine that for this one, you want to save the array, the original one, and you want to save a mask, and you want to only operate in the circular region. So there is Numpy has a module that's called mask arrays that can, in one array, in one object, you can have both the mask and the data. And you can, if you, for example, do the mean of that array, you will only consider what is in the mask, which can be very useful. So these are advanced topics. So we include them there, but now you know that. Given the time that we have, that's what we did. And there's also other extra resources, documentations, and tutorials. So yeah, that's for today. Do you have any questions? No? A lot. It was a lot today. Yes, it was a lot today, and I think you deserve a break now. Yeah, so that's it for today. Yeah, that's wrap up for now.
Well, just a comment about it. So in the solution you gave for the observational cluster, so we solved everything in one time. The NP, QRT,
right.
So in terms of readability,
yes,
and that kind of stuff, but we discussed.
Yeah, you can definitely. Yeah.
Yes.
I did it, so there's not too many. But definitely.
You mean this part?
Yeah,
this part.
that's right.
Yeah.
The thing is that everyone has to be there. In this sense, I find it readable.
Yeah, I mean, it's just the broadcast is that it's going in the back, that makes it correct.
And that's what we do. That's what we did the broadcasting exercise. Because if you read this, you know, if you encounter this in your colleagues' code, you really don't know what's happening with the changes. No? Yeah.
But I mean, like, I didn't emphasize on it, but broadcasting is used in every Numpy lecture, right? Everything is just broadcasting in some way, point or the other. So that's why you can do the single line thing. So yeah, if you see people doing it, it's enabled. It's not just for like a of the operation, but every operation that is. That's it.
Any other comments?
It's a good point about it. Very good point.
Any other comments?
Run away.
Stay tuned.
So guys, before we leave, so we managed to finish on time today. That was great. Tomorrow we have planned a social gathering. We will go after lunch. We will have some first lectures in the morning, and then after lunch we will go to the Biodiversity Museum. For us. Then we will have some time to hang out and yeah, not just focus on the work, but try to mingle and get to know each other more socially. So yeah, that's for tomorrow. See you at 9 o'clock again, just like today.